Hi, this is Nilay again. Today, in the second vlog of the Impact Radar examples, we are going to look into the data-driven enterprise and how it materializes in context of AIOps and what is the impact that it could leave for next 5 to 10 years and what we're going to see. So before we deep dive into that, this is going to be, again, a little bit of lengthy video. So take your time, maybe have a coffee and watch, or save it and watch later. Right. So let's go back on data-driven enterprise. Based on this impact radar, which I have built, it consists of all components: edge, machine learning integration, observability, data democratization, sustainable and cost-effective data management. It practically comes in center. It is an intersection and implementation of everything. And today we're going to see that if we pivot into AIOps, how it is going to change the day-to-day development lifecycle that we see from developers' perspective. Well, before we deep dive into that, I'll set a context with a problem which inspired me to do this video as well. So a couple of months back, roughly around 6 months back, one of my friends who is currently running a very successful AI startup reached out to me and suggested me that they are running out of an option to identify, to understand a problem with their AI model and why they're behaving in a certain way with high load or high intensity compute. Surprised me because I know the person personally very well, and they are really good engineers. And I said, like, if they have not able to solve it, how I can solve it? But anyways, there is always a writer block, there is always a developer's block. So it's always good to take a second opinion and understand like how to solve the same problem with a different approach. I started looking into their code. I started looking into their execution. Technically, I cannot find anything. And then suddenly the idea pops into me and say, hey, why don't I just use some smart machine learning AI algorithms to validate what is actually happening behind the scene? What is a CPU profile looks like? What is a bytecode look like? What is a memory profiling look like? How their functions are executing? And that brings the whole idea from my previous ice tray, which I think something POC I had developed a year and a half back on research perspective. I brought that toolkit out, enhanced it, and then I used that toolkit to understand their problem. And bingo, we were spot on. And the problem that we were not able to identify, including myself, using my human eyes, human ears, my human gut feeling, and my human intuition, AI has identified pattern practically within a half a day. It was a lot of bytecode to chunk about, but it landed us to the spot. We can say it's maybe a luck to an extent, but not completely luck, because AI is a probability-based engine, and that means it has identified certain probabilities and behavior that why this goes wrong. And today, exactly, we're going to deep dive into it, which increased my interest, and I took that forward. So then onwards, I enhanced that framework and I enhanced that toolkit to be used internally for permanently into MLOps and the quant model ops. So because MLOps and quant, they both required a good computational performance, and this toolkit helps me to understand, like, when I'm serving my models, what should I look out for, how should I configure things, etc., etc. So without wasting more time, let's deep dive into it. So to demonstrate today's problem that we discuss, I have basically wrote a couple of sample programs like simple Python files with multi-threading, multi-processing, locks, asynchronous processing, and everything. Like practically the good, bad, ugly, everything I've thrown in there. And also I have written like a test model just to demonstrate, like, okay, when I'm training this model, what I get out of it. And for detection, I've written 2 notebooks, and I'll be walked through that 2 notebooks as well, to understand like how AI is going to impact us in the coming future. But before that, one of the key tools that we are using for this particular experiment is a Pyroscope. And I think Pyroscope is a very famous tool, everyone aware of it. How do we use, I'm not going to deep dive into how do we use this tool, but some maybe point later I'll make a detailed video to say what are the better ways to actually profile your code into Pyroscope as well, but not in this particular session today. So let's deep dive into it. So all I'm running this particular data, which is generating randomly a lot of wait times and processing data, and creating the CPU locks, and trying to generate the bad practice and the good practice both ways. And with this Pyroscope, I have created 2 applications, which is one is a model serving and one is a model training. And they both are being tracked for last 30 minutes, 35 minutes together. And as you can see that when I'm looking into this code, it tells me actually very well that where are my CPU. And by the way, in this particular demo, we are just going to see the profile from the CPU point of view. But if you really are interested into like extending this to a really sophisticated tooling, you probably would need to look from many perspectives. So like a Pyroscope server itself, look from CPU, block counts, duration, and all sort of stuff. And if you're using GPUs and other thing, I think you would also need to identify like how you can get those counters and everything in there, which was a tricky with Pyroscope. But somehow I managed when I was doing that research for one of my friends. So in this particular one, very straightforward. It's not a rocket science there, because I want to keep it very simple. The idea is to explain the theory. Idea is to explain the approach, then giving you a solution. One other thing which I think might be useful to mention in this video is, during my research, after that, I have helped roughly around 6 or 7 different companies till this date to help them to optimize and identify the true problem in their quant algorithms or machine learning algorithms. One thing I can definitely say that there is no one common AI model that we can build that will work on all applications. And I think that might discourage many people and say, how come? Because AI is AGI. Of course, there could be possibility that we could build in future, maybe something like that. But the real challenge that I saw with the common purpose model is it does not pick up the right level of intricacies and the feature extraction from our code, because every code is a different code. Every application is a different application. It's been restructured differently. Underneath framework might be the same, but the code is different. So it is highly recommended to get some meaningful outcome of your algorithm. It is necessary to do some basic annotation and self-training of that model. It's not hard. Means I was able to successfully do the self-annotation and training within a half a day or day, and then it remains permanently with you. So like use like a unit test. When you change the code, correct it, use it, correct it, use it. It just becomes the part of your life cycle. And now, actually, it is part of life cycle that wherever I have set up the MLOps pipeline for those kind of a significant problem issues, the AIOps is part of it. It is not a luxury. It is like a DevOps, as I said earlier. And we will walk through when we run this, like why I say AIOps is next DevOps, or it is a DevOps plus. So yeah, it's a Pyroscope. It is constantly measuring it, and I'm extracting data out of it for my models to validate Now let us see like how the comparison works. So as we see this particular comparison, how it is working, you can see that yeah, there is a difference, right? There is a difference. This particular function supposed to be 0.76. Now it is 0.65. So even if I basically do the like a little bit of a 2 hour speed here, right? Yeah. If I take it like this way, right? And I can clearly see now, oh yes, there are some significant difference. And what this difference help us to understand. Number one, when your machine learning or model has been published, you can actually validate the model profiling, model performance alongside with model accuracy. So now it is not about just business validation with how accurate your model is. You can actually validate whether your model is performant or not. And I give you a very good example. Um, um, one of the city's quant company, quant based asset management firm, reached out to me a couple of months back as they would like me to just look into the quant model and say and identify a problem to understand like why the back testing is like a perfect, but when they put into the market, it is not performing. And of course, we put all those data capturing and all sort of stuff, and immediately we figured out that model is accurate because it is statistically improved version of the previous one. But the model execution time was increased by 200 to 300 millisecond on an average. And within that 200 to 300 millisecond window, they used to lose opportunities that the earlier model used to pick it up. So performance or accuracy doesn't mean a profitable model. And especially the like if you are e-commerce website, right? You are doing the fraud or risk and all sort of stuff. You have to be on the real time. If a fraud has been identified after 2 minutes, once the order has been confirmed, the something has been processed or etc., you may lose the money because you have now reserved something for that fraudulent order, and which means your actual customer is now missed out on that offer or something like that. And now if you correct it, you put it back, eventually you will see that there is some revenue loss around it. So this problem is not specific to market. This problem is very much common across the industry where you need decision at the real time. So this kind of AI-based profiling is extremely important if you want to build that cutting edge or competitive edge over your competitors. Now, going back, like this is a basic thing. Like, okay, let's capture everything, and then what we have done is we have built this anomaly detection. And before we go, let me quickly walk through the architecture that generally I have defined as a very simple architecture, where this kind of a model has been built on the previous execution using business telemetry and compute telemetry, where the business telemetry tells you if certain events are happening or if certain scenario which would imply certain kind of behavior. And compute telemetry is like a basic bread and butter, CPU, memory, blah, blah, blah. Let's put into the dry run, run that thing with the CPU profiler, train, backtest your model, and then release your anomaly detection engine there. Now, how we use that? Every developer that push the code, it should run as a Git pipeline or whatever the pipeline that you put in as a CPU profiler, generate a sufficient profile, let's say 5-minute profile of running it, or test with the unit test and all sort of stuff. It profiles it properly. And then the profile has been sent to anomaly detection. And what it does, it actually validates against previous execution. And with this particular anomaly detection, as you see, and if I have to show you the output of this detection, this is exactly what we did, is identify the correct function position and all sort of stuff, and all the functions here are their flame bearers and then their positions and all sort of stuff. So what it does, it looks like it's unreadable, honestly, but it makes sense. So it basically makes sense, all the functions that you have created there. So let's say, for example, I have created send process, create manager, or there are a couple of let me find out my own async data processing, let's say, for example. So async data processing is here. Yeah, here you go, async data processing. So for example, what I'm trying to say is it's a very good, it's a hard to read, but it's very easy to picturize, and it actually identifies the individual lines or certain segment or a depth of calls which are actually using the CPU ticks. So these are the CPU ticks used by each and every part of it. And this many ticks of CPU can be easily vectorized and validated using, let's say, CNN algorithm, using a KNN algorithms, where you identify using appropriate graph theories or cluster theories that what is happening. And you can actually build some tolerance as well and sort of find out, like, if it is a new function has been introduced, you ignore it and sort of thing. And that will bring you a very genuine outcome from that particular action. And it will tell you if code is badly written. It will tell you if there is a significant difference. If there is a difference, that does not mean it's bad code. That means there is something that has changed. Now, it has changed for a reason, or it has just changed by accident. So that's what we need to find out afterwards. And this particular process help you to pretty much automate your high and complex and highly demanding workloads to remain very much accurate. Now, going back to the original example and where it all started, the whole journey started 6.5 months ago, in a kind of a serious way. In this whole process, we actually help them using this to reduce, improve their CPU consumption by approximately 1/4, or in a general, roughly around 25 to 28% on an average. Now it sounds like, okay, that's nice, but how much money, cost, effort, and everyone spend the time? Actually, it's only AI we just found. We just followed up based on the AI's lead, and it doesn't take us too much time to identify. It was the earlier that we spent a lot more time and we couldn't find anything practically, but the later we found things. So now that company serve roughly around 1 million requests a month to their customer, and their individual request roughly cost them, let's say, for example, I'm giving you a rough idea, means that does not mean that cost them that much. Let's say you have 25p or cent wherever you are in the world, whether it's a 25c or 25p, is your one request cost to process a one AI task that your customers are asking for you. And if you improve that by 25%, which means a per request is actually now costing you 6p less. That 6p multiplied by 1 million requests, 2 million requests, 10 million requests. If you're a big, then maybe 100 million requests. That is a lot of money. And this is why it is quite essential for us to understand sustainability and cost-effective data management. And that's why I said that has to be part of this exercise. Otherwise, it's pointless. So going back on this architecture, this is exactly what it does. It picks up from your development lifecycle. It picks up from AIOps. It picks up from production. So let's say something has been identified in production and it's sent to anomaly detection and it automatically identified by AIOps. Now your AIOps become intelligent decision maker, which will not just raise event tickets for your support team to look immediately into it before it can happen, but it will also ensure that it can take some decisions based on earlier architecture that we say like MLOps optimization, and it identify that CPU usage appears to be not very good. Then it can send a signal to this live optimizer, say, you know what, this scenario is happening, the CPU leakage or memory leakage is happening. Can you make sure that I would have 2 more nodes for sake of making sure that my SOA always remain. Now, we can say that we are provisioning 2 nodes based on this probability, but bear in mind that if this probability is high, and that means the system could go to the crash or failure or restart, and in that period of time, if you lose your business, that will be much more costly than having the 2 nodes running for 10 or 15 minutes to cover up that period until the support team or AIOps can actually calm down the situation there. So what it brings together, it's that combined ecosystem where AI is detecting a problem, predicting a problem, bringing human intelligence into it, and also trying to safeguard the overall quality of service within your organization. And how that all started? That all started from that AIOps culture. And here we are coming back again to the point that AIOps culture is equivalent of the DevOps culture, because this is the same impact that DevOps culture has left with us. Automation, fast releases, a full stack team, anyone can deploy, SRE, everyone supports, everyone develop. So AIOps is now in that same category with the next generation. Everyone is watching, everyone can intervene, everyone understand, and developers are smart people. They can easily accumulate the knowledge sufficiently to operate in this kind of a ML environment. And that sounds pretty good, in my opinion, that if a company or if a business is not looking AIOps seriously, I think they're going to struggle in a way, because if you look at the Gartner's report, which I opened, the second top trend after the cloud data ecosystem is the edge AI. The third trend is responsible AI, and responsible AI means also risk proportional approach, and not just risk proportional approach, but responsible AI also consider is ecologically friendly AI. You don't want to spend 25% of extra compute on unoptimized code as well. And the most important thing that we see, data-centric AI. This is exactly the data-centric. So you are backing up with your profiles and everything, and making a very informed and calculative and mathematical decisions around it. So, well, that is about sort of a talk, and then I'm probably gonna jump very quickly into like, okay, let's find some problem. So I have written a very basic model here, very basic probabilistic model, no funny thing, no funky thing, and all it does, it processes 3, and it identifies me based on these 3 given parameters, 3 given inputs, which are these inputs. Which areas should be my consideration? So it's an optimizer. This is Python file. This is the same Python file is put into this one, just for sake of better visibility. So if I run them all, so it's the whole model has been executed, and there you go, it's been executed. Yep, done. And we see that it has told me that, okay, I see these are the areas you should look for, and it appears to be like correct. because it's a random. That's why it's coming through random. But they're pretty much pointing to some of the critical failures which we're discussing. And this file is anomaly detection, and the same way, all it does, in this case, it takes two historical files, use the model, and also use the target file to basically process, and tells me from the target file what it finds which does not satisfy my threshold. Now, this is a very basic thing, by the way, but it just to show you the concept around it. The real models has to be built with far greater accuracy and annotations to get higher and better results. And I'm actually being lazy. I'm just showing you the concept, that how we actually implemented for a couple of clients. So from a theoretical point of view and from patterns point of view, I'm not trying to hold back anything. But of course, if we unveil the real model, we actually are unveiling the cost that occurs to our client, and that's why, unfortunately, I'm not able to share the real models or what we have done with the real models. But this certainly will give the sort of a in-depth understanding of the process and the idea where we are taking it forward. So yeah, thank you very much for looking into it. I'm going to deploy this code as open source somewhere. It will be available in the document. It will be available in the description. Please feel free to watch, and have a good day, evening, and keep subscribing me. And thank you very much for your support. Good luck.